This is 23.12 parallel circuits. Today we're going to talk about how to draw and solve parallel circuits. In series circuits, you learn to calculate the total resistance by adding them all up because they're all in a straight line. In parallel circuits, they're in loops. You can't just add them all straight up like you normally would. They're a little bit hard. Instead, you use this equation. So 1 over the total resistance is going to equal 1 over each resistance that you have. So 1 over each resistance. It does look similar, doesn't it? Maybe for sure. But it does look like the one we just did in chapters 17 and 18 with the 1 over F equals 1 over P plus 1 over Q. Same idea, just with resistors. So I'm just going to walk you through a little small calculation of that. Let's say that we have 3 resistors. One is 10, one is 20, and the other one's 30, just because we can. In your calculator, you're going to go 1 divided by 10 plus 1 divided by 20 plus 1 divided by 30. It'll give you some sort of number. This is not the answer. Very close to the answer, though. Flip-flop, the bottom and the top. 1 over 0.183 is going to be your R total. So in your calculator, 1 divided by that answer you just got, and you'll get 5.45. There's your R total. So there's a little example of how to work that equation. You're still going to use VER and PIV, so that doesn't change.
Does that mean power stays the same too?
Uh-huh. Okay. Now the rules for parallel circuits are a little tiny bit different than they are for series circuits. So I'm going to write the rules up here. For parallel, we already know that you calculate your resistance inversely. This is an R, by the way. Sorry. Your current is no longer constant. Instead, your current is added. And your voltage is now constant. So those two things switch around. So we're going to start out with a practice. Here's my practice. We have 3 resistors. They're in parallel. We know they're in parallel because they're connected by a junction. That's this little T branch here. So this is a junction and this is a junction. So it's got to be in parallel. Our resistors are 1 ohms, 2 ohms, and 3 ohms. And we have a 24-volt battery. I'm going to draw that right here. I'm just going to redraw. Again, you probably don't need to do this, but it's good practice for later. So this is resistor 1, 2, and 3. And our battery is 24 volts. So draw your table, making that really terrible noise, VERP. And there's 3 resistors, so we're going to do 4 columns. 1 for each resistor and then a total. Okay, we're going to fill out the givens. We know resistor 1, so R1 is 1 ohm. Resistor 2 is 2 ohms, and resistor 3 is 3 ohms. Now that just happens to be for this problem. It doesn't always end up like that. It could be any number. And the other thing that we know is that the battery, so this is total, sorry, this should be saying total up here, is 24 volts. So put 24 in. Any questions getting the setup done? So we're all good. We're all on the same page here. Okay, so now we need to add up our resistances. So 1 over R total is going to be 1 over R1 plus 1 over R2 plus 1 over R3. Now, if we had more resistors, then it would be plus 1 over R4, 1 over R5, and so on. So let's plug these numbers in. 1 over R total is going to be 1 over 1 plus 1 over 2 plus 1 over 3. Get out your calculator.
Okay.
1 divided by 1 plus 1 divided by 2 plus 1 divided by 3. Unless you have a one-line calculator, and then it's going to take you a little bit longer to do that.
Just quit.
Just give up and take one of mine instead.
I'll just copy it.
All right, this is going to be 1.83. You're not finished. Flip flop the bottom and the top. Give you our total. And what's nice in these calculators, 1 divided by answer 0.55. So let's put that in here, 0.55. This R total is also known as equivalent resistance. Same thing. What is the resistance of the system? What is the resistance of the circuit? Or what is the equivalent resistance? They're all talking about that number right there. All right. When you were doing the series questions from last night, what was the next step? After you found total resistance, what did you do? Find the total current. So we're going to figure out what this number is here. We're going to use VER. So V total equals I total R total. Put those numbers in. 24 equals I total times 0.55. $43.6. Okay, on your series questions last night, what was the next step? Nope. There's more before that. Fill out I. Okay, so why did we fill out I in series? Because it was constant. So we can't do that here because V is constant instead. So we can just take that V and spread it out. So if it's 24 here, it'll be 24 across the entire system because the entire system is in parallel. Okay, now what do we do? solve for I. So we're going to use V equals IR on each one of these. I'll just show the first one. V1 equals I1 R1. 24 equals I1 times 1. Plug it in. 24 is going to be I1. So this one will be 24. This one will be 12. And this one will be 8. Now what do we do? Now we find the power. Okay, we're going to use PIV equals IV. I'll show the first one. P1 equals I1 V1. So P1 is what we're looking for. I1 is 24. And V1 is also 24.
Let's get the PIV.
$576. So do that for each one of these. I won't write that out. Including the total. Now I know that you probably don't need to use the grid for this problem. You probably figure it out on your own just fine. But when we do combined circuits tomorrow, this is going to become very, very important because you'll see that this problem will take up the entire board. I don't know how I'm going to make it work with the E-beam since the E-beam cuts off half my board, but we will see. Okay, so you need to double check. Again, you probably don't need to double check with this because it's pretty easy. When we get to the combined circuits, double checking is going to be really important. So to double check, add up the bottom and make sure it is indeed the total. Now with this problem, when you add it up, you actually get 1,056. That's okay. The reason that it probably is not perfectly exactly the same is because here we rounded to 0.55 and here we rounded to 43.6. So depending on your rounding, that's going to change it up a little bit. And that's okay. This is close enough, so you can still see it's fine. If you were doing this on the test, anything between this range would be okay. Any questions on this? Okay, so you should have your clicker. I'm going to give you another circuit, and you're going to be asked a whole bunch of different questions about this particular circuit.
I have a question as well.
You can't have the question. Turn around. Go
Are
ahead.
there any truly solid things that are also transparent?
Solid things that are also transparent.
Like glass.
Like glass.
Which you said was a liquid.
How about diamond?
Yeah, but you can't
I'm
really
just
see
wondering
through
why
it.
some
It's
things
like
are
it's
transparent.
Maybe you haven't seen a real diamond.
Wow, I don't think I would.
Why are some things transparent and other things aren't transparent? Why is human flesh not transparent?
Why do you think so?
How do I
This
make
is chemical property.
myself transparent?
Chemical property. Why is red red?
Because it's red.
Got a chemical property, and it's vibrating at a certain rate that reflects red light. Actually, it has to do with resonance with light.
Yeah, but how do you vibrate to let light pass through you?
Maybe because it's, if it,
You shake yourself really
okay,
fast.
light is very, very small in the electromagnetic spectrum. So if the molecules are not vibrating within the light range, they can't reflect any color. So they must be vibrating on the ranges outside of
So
the
we have
light.
to shake ourselves really fast.
Well, within the right.
I just want to know how I get
Yes.
What is
To do what?
1,046.
1,046. I went 24 times 43.6.
3, 12, and 4.
Oh, it crashed on me. No.
Don't kill me. That happened like 3 minutes.